organizers, and all the talks so far have been really interesting. So as I said, this is we're here to talk to you about NEPTUNE. So my name is Dudson at the University of York. So I have a background in plasma physics and fusion research. This is a project led by Rob Akers and Wayne Otter at UKAEA, which is one of the two high priority use cases under ExCALIBUR. I lead one of the main work packages under that project. And it's one of the main aims is to try and integrate all the different components. As I'll talk about shortly, it's a new code. We're trying to integrate as many of the ideas and the things we've learned and the communities have learned over the last few decades to build a new set of tools that we'll use to design, operate, and analyze sort of next generation of fusion devices. So I'm here basically to learn about what's been done outside fusion. And what I hope to do here is to give you kind of the context, the background to try and explain how we see we can take some of the ideas that have been developed outside fusion and adapt them to our problem. As part of this, I'll try and explain what the constraints coming from the physics are. So there's some very challenging problems, I think also very interesting problems. And so one of the other aims of this is to try and encourage you all to give us feedback, ideas. We have some sort of initial thoughts on how this would work, but obviously looking for improvement, and to try and encourage all of you to get involved in this project, because there will be a series of calls and funding coming out connected to this. So this all fits together as part of what we call a co-design effort. So we're aiming to, as Peter said, integrate uncertainty quantification from the beginning, and to try and make sure that as we design this code from the ground up, that we're taking on board all these ideas and we're not shutting off opportunities in the future. So it's aiming to run on Exascale hardware in the near term and for the next 5-10 years at least, because these codes tend to have a very long lifetime. And so performance portability that was just discussed is also one of the key aims. Okay, so this is a tokamak. It's the inside of JET, operating in Cullen near Oxford. And I was going to talk through some of the components and some of the things we have to try and model when we're trying to model this whole system. So the aim is to try and either use it as a kind of flight simulator for something like ITER, which is currently being built, and for post-process like analysis of and interpretation of the experimental data, but also as a way of designing new machines. So we want to be able to integrate the simulation of the physics processes with the design of the machine itself. And so we need something which runs fast enough to be part of an engineering iteration cycle, but also brings in all the details of the walls. And as we'll see shortly, small details can have a surprisingly large effect. So this kind of amplification of uncertainty is a major problem that we have to deal with. And so here I'll just try and give a flavor of what processes are involved. So on the right-hand side of the picture, you can see a kind of photo, which has been when the plasma is operating. On the left is when the plasma is not running. And you can see that the bit in the middle, the bit you can't see, is the hottest part because it's radiating in X-rays. So if you could see in X-rays, you could be lit up, but it's not. So this is about 100 million degrees. It's almost collisionless in that particles can freely stream around the machine many times without colliding with anything else. And so those particles are moving at a good fraction of the speed of light, and they can move throughout the entire domain or over a very large part of the domain in a very short time. It has very small fluctuations. So in order to keep the heat in, we need to try and make sure that heat is not being leaked out through turbulence or other processes. And so the fluctuations are small, and for those fluctuations are extremely important. So we need to be able to resolve and accurately calculate fluctuations of the order of 1% or less, and to be able to work out what transport they will produce. And so we're looking for accurate calculations of small fluctuations in fairly large quantities. So the bits you can see in this picture are the bright bits at the top and bottom. This is where the hot plasma is meeting gas. So neutral gas, which is either recycled from the walls. So when plasma heat hits solid surfaces, The electrons and the ions recombine and it forms gas, and that gas then comes back and interacts with the plasma again. And what you see here is the electrons in the atoms being, through collisions, being ripped out and then dropping back down again and radiating. And this radiation and interaction between the plasma and the gas is a very tightly coupled system, and is also vital for fusion reactor design. So one of the big challenges is the power loads on the walls of the machine. So this, if you don't do anything, well, if you make particularly bad choices, this could end up as sort of gigawatts per square meter power loadings on the wall. The design limits are about 10 megawatts per square meter, and so achieving this requires a combination of the physics of this interaction between the gas and the plasma, and also a careful design of the shape of the wall. So you see it has all these kind of dips and this kind of shaped wall if you look near the bottom of the machine, where essentially the plasma is meeting the wall at a shallow angle. So that has the materials, of course. At the bottom of the machine, this is tungsten, and at the sides is mainly beryllium. The sputtering and the loads on the erosion of this surface is a major input to things like the design and the lifetime of the machine. So that's something we want as an output. But it also has a big impact on what the plasma is doing, because things like when a particle hits the surface of the material, whether that particle is reflected or absorbed or scattered actually has quite a large effect on the kind of plasma solutions you get. So it's a two-way process. The wall is affecting the plasma, and the plasma also affects the wall over a long time. And finally, then we have things like the heating systems. So on the walls, you can see these kind of striped pattern that are pointed out here. So these are essentially like a microwave oven that are injecting megawatts of microwave energy into the vessel. But where that microwave energy is absorbed is dependent on the plasma solution. So if you have a plasma with a different shape or a different current profile, then the energy is absorbed in a different place. And because that energy is absorbed in a different place, that in turn changes the plasma. And so there's kind of these two-way couplings between many of these systems. And this all takes place on a very wide range of time and spatial scales. So you see at the short scales, we have the frequencies that the particles orbit their field lines, around down to almost 10 to the minus 10 seconds. And on the high end, you see the kind of timescales that we're trying to run to, so thousands of seconds or tens of thousands of seconds for the pulse length. There are a series of processes which occur on these kind of timescales. At first sight, this might seem good in that you could say, well, there's this great big separation of timescales. Surely we can separate these models and couple them together. Unfortunately, there's usually not a very good separation of timescales, in that many of these processes have strongly overlapping timescales. And if you do two separate simulations and then try and combine them, you find that the results are not the same as simulating them all together. Similarly, for the parallel, like the spatial scales, down to sort of fractions of a millimeter up to here, sort of kilometers. Obviously, the machine is much smaller than a kilometer, so this is the things like the mean-free path. So because it's a torus shape, the field lines form these helical spirals, and particles can travel many kilometers along those field lines as they wrap around the machine. So to try and model this, there are a series of different mathematical models that have been constructed. The most uncontroversial is just essentially Newton's laws and Maxwell's equations. This is what we might call a fully kinetic model. So just following individual particles around on their orbits. If you remember, these orbits are really fast. So this is kind of 10 to the minus 10 seconds it takes for a neutron to go around in its orbit. And so your timescales end up being some fraction of that. So you end up with almost down to picosecond kind of timescales. It's slightly better for the ions. There you have kind of gigahertz kind of frequencies. So these are generally not done. There is a paper out just the end of last year where this was done. So it's a six-dimensional system. You're evolving the position and velocity of all the particles. And the problem is this requires time steps of about picosecond. Again, you have to run for some fractions of a millisecond at least in this case. But these kind of models are used and they are necessary in some cases. Examples are the one on the far right. So this is a fast alpha particle. So it's the product of fusion, produces these very fast ions. And you can see their orbit is a good size or a good fraction of the size of the machine. And so here you do need to follow the whole particle orbit because that orbit is non-trivially kind of circle. So yeah, you need to follow the full orbit in that case. The other case is neutral particles, which is the colorful one first from the right. And here all these different colors are different species. So it's different, in this case, carbon or beryllium, tungsten, you might have nitrogen, neon, all these different molecular and atomic species that need to be followed. And because the density is quite low, these are essentially collisionless. It's like a rarefied gas dynamics, that they just travel in straight lines, essentially, without colliding. In many cases, we can average over the fast timescales, and this gives something called gyrokinetic model, where essentially we're following loops of charge rather than point charges. This is quite widely used to study turbulence in the core, and sometimes increasingly now in the edge of tokamaks. There are approaches using continuum, where you have it's now a 5-dimensional grid. So you need to resolve 3 dimensions of space, and you also need to resolve 2 dimensions of velocity. So that gives you a 5-dimensional system. Or you can use a pig code, so particle following kind of a code approach. And this was recently coupled in a paper published this year. Further doing this kind of model order reduction, we have this so-called fluid models. So if there are sufficient collisions between particles, then you can assume that the distributions are driven towards Maxwellian, and you can start to apply some of the 3-dimensional fluid models. They look a little bit like Navier-Stokes, but typically a lot more complicated. And these can be used in some cases to study the turbulence. So these are supposed to be individual eddies here on the right, so the crude picture. Further reducing even further, we can make some approximations as to what the turbulence looks like. So if it's a diffusive process, for example, then we can assume some kind of diffusion coefficient, and you can average over those kind of turbulence timescales. And these we might call a transport model. Okay, so now I want to give some examples of coupling that has been done and is done currently. This is probably the most widely used and probably most important in terms of the fusion program, something called SLPS. So this is what's used currently to design fusion reactors. So it's used to design ITER, for example. It's a combination of a fluid model, a transport model, in fact. So it assumes diffusion for the transport. So on the right here, you have these different grids. The kind of green one is for the plasma. So this is aligned to the magnetic field. So because the particles stream very quickly along the field lines. And then the triangular one is for the neutral gas, because the gas obviously doesn't care about the magnetic field. It just travels in all directions. So here, this is a fluid model coupled to a Monte Carlo model for the neutrals. And there are some tricks needed here because as often in fusion, there's a very careful balance between some very large flows. So you have some very large quantities. In this case, it's inputs and outputs, and the flow of neutrals around the system. And there's a very small difference between them, and that difference is important. And if you're not careful, this is just swamped by the noise. And so the plots on the left are essentially without correction, and the purple line is in this case the flux of helium. But and what you're trying to achieve is the difference between the 2 lines that you can barely see, because they're just swamped completely by the noise. Whereas in the middle, you can see the noise being suppressed, and now we're able to resolve this very small difference between the flux and what's going to the pump. And this kind of difference would then be important for how you design your pumping, how you design important parts of the machine. This can be made slightly more sophisticated in terms of the transport. So this is something that's been tried a few times. This is an example where we want to try and predict what the transport will be. So if we know what the diffusion looks like or is, then we can obviously put that into the model. But for making predictions, we don't know what the turbulence will be. And so we don't generally have a good estimate of what parameters to put in. And so what you might do is take the SLPS simulations that I showed previously, and then run this together with the turbulence code, in this case, BUF+, And then we essentially run the turbulence code to adjust the diffusion coefficients. And this might be run in a kind of alternating, so this is supposed to show in the middle, where you're running the turbulence code for a short time, use that to calculate a diffusion coefficient, use that diffusion coefficient to advance the transport over a longer time scale. And then, because at this point the turbulence will have changed, you have to go back, adjust the model, and repeat. And this is essentially a crude kind of physics-motivated surrogate model that you're using a diffusion process as a surrogate for the turbulence model, and then using that to integrate it into a bigger model for the transport. This is something that we want to try and improve and sort of build on. This works. I'll skip a bit faster. This works in the core plasma in some cases. There's just another example where this has been done, where if the turbulence is sufficiently small scale that you can separate it into disconnected regions, you have these kind of stripes in blue where the turbulence is solved. And this forms a kind of a coarse grid in space and time where you can calculate the turbulence, and then you can use that to advance a longer timescale transport model. Unfortunately, there are some features of the edge plasma, which is what we're trying to solve, where the plasma meets the materials, which make this very hard to do. So on the top left, you'll see that it's a plot. This is essentially a measure of the flux of particles arriving at a probe that's been put next to the plasma. And you can see that the fluctuations are about a factor of 4 or 5 larger than the average. So we have very large fluctuations, and it's the extreme values that are doing most of the damage. So you really need to know what those extreme values are, and you need to run a turbulence model for long enough to find them. In the middle, you can see this is a results from simulation where it's showing that there's essentially no relationship between the flux of particles and the gradient, which you'd expect if it was a diffusion process. So if this was diffusive, a straight line should be a good fit. In fact, it's a terrible fit. And so there's been some work recently, which we'd like to extend to essentially find better models to use as surrogates in our transport models. And finally, there's this problem of how you couple turbulence codes which are simulating slightly different regions. And here the challenge is really that the fastest coupling is through the electromagnetic fields, because plasmas are charged, well, the components of them are charged. They feel the electric and magnetic fields, and so if you have a small change in one location, that electric field or magnetic field propagates a very long way, sort of speed of light, really, and can affect essentially your entire domain. And so this coupling tends to need a kind of overlapping regions, and this brings in all kinds of problems of how you ensure conservation properties, particularly since you really care about small differences in large quantities. Okay, so finally, I'll mention just very briefly, there's been a lot of work and several attempts, many of them failed, to try and integrate all the different legacy models into one giant framework to rule them all. There was a whole series of proto-FSPs which tried to do this about 10 years ago or so. Most of them were a bit of a failure. The one that was really successful is the one that didn't do any coupling and just integrated everything into one code. More recently, there have been some more successful attempts. OMFIT is one of the ones in the States, and there's an ITM integrated transport modeling for ITER. So these essentially take existing codes, so legacy codes that have been around in some cases for decades or 50 years in some cases, and try and wrap them up in a nice interface and then couple them together.
Sorry, Ben, 5 minutes left.
Okay, thank you. Okay, so finally come on to the kind of challenges. I've mentioned a few of them as I went through. I'll just try and summarize that we're dealing with a whole lot of different physical models. There are lots of different processes that need to be integrated with each other. Because of the way these models behave, we often need different grids. So the plasmas are highly aligned to the magnetic fields, and that needs to be exploited for efficiency. But at the same time, other parts of our models don't care about that alignment, and so they need a different kind of grids. So let's see. So this is an example. This is from this paper here, looking at kinetic models. We have different regions of the grid where this is something called Dudson number. So if it's bigger than 1, then it's a kinetic kind of model. If it's less than 1, then it's a fluid-like model. And you see over this grid, which is for eta, the neutral gas goes from essentially highly kinetic, so very long mean-free paths, down to highly fluid-like. And the regions of the grid where you need to treat models in different ways changes in time. And so this can be quite difficult. Yeah, said that. So there's a lot of different overlapping scales, and you try and treat this implicitly in many cases. One of the strongest coupling is the global coupling due to the electromagnetic field. This essentially means you need to solve an elliptic equation at every time step. And if you don't do this, you end up with timescales which are sort of picosecond or less, because you need to then resolve such the speed of light, as this ends up being such prohibitively slow. There are a few places where we need to resolve very small differences in large quantities. A kind of crude way of thinking about this is that the individual forces on the plasma are of order of meganewtons. The whole plasma only weighs a few grams. And so if you want to keep it there in steady state, there needs to be a very good balance between all these very large forces, or the whole thing will just very quickly hit the wall. And this can be studied in this form of singularly perturbed problems, and AP schemes is one approach. Finally, there are some unique problems linked to going to exascale. So all the challenges I mentioned previously are challenges for existing models on existing hardware. Those will still be there. Exascale then brings in further challenges which we need to try and think about and how to get around them. One of them is this problem of having an increasing number of cores or multi-GPU systems, thousands of GPUs, and then those need to be coupled together potentially on very short timescales. So because every part of the domain is tightly coupled to every other. And so we need some way of breaking this tight coupling. One of them, which looks promising, is kind of focus of our thinking currently is to use surrogate models, because as part of an implicit solve in one part of the domain, you need to have a good model for how the rest of the domain will respond. And so surrogate models provide some way of potentially at least giving that implicit coupling and enabling higher, large time steps, whilst perhaps being trained on the fly. So using the data that's being run asynchronously, train the models, and use them to kind of separate this tight coupling. I'll just give it that in. And the last part is, which I don't think is mentioned so far, is just handling all the data and be able to do in-memory analysis and reduction of the data. So this is an example from an existing code. Actually, this is a few years ago. XGC is a PIC code. So they evolved for their ETA runs about 640 billion particles. And so a single checkpoint is about 100 terabytes of data. And the turbulence run can easily make 100 petabytes of data per day on a current machine. So these are very large quantity of data. Obviously, most of it you don't really care about. In fact, in a few cases, you might care about a handful of numbers. So out of all of those petabytes of data, 5.5 of them are important. So you need some way of reducing the data in memory, avoiding writing, and obviously making sense of this data as it's running is important. Okay, so I think I'll stop with the conclusions. Say that there are a lot of interesting problems. It's quite a challenging system to try and solve because there are these very strong couplings between the whole system. There have been lots of attempts and lots of ideas that we're building on. Currently, we're interested in surrogate models as a way of breaking tight dependencies between systems, and also because they provide potentially a way of doing UQ and sensitivity analysis on the system. So there are lots of problems to solve. If you have suggestions, I'd really like to hear them. And obviously, if you want to be involved, that's also very welcome. So thank you.